Then next topic we'll go to MOSFET. We will go to MOSFETs today. MOSFETs means metal oxide semiconductor. Metal oxide semiconductor. And in that we have different types. That the first type we are dealing today is enhancement metal oxide semiconductor. Enhancement. Let's go to the first one, comparison between JFET and MOSFET. In JFET, input impedance is high because input is reverse biased. Whereas in MOSFET, input impedance is high, much more high, not because input is reverse, but because of silicon dioxide layer. Input is reverse biased in JFET, whereas in MOSFET, we can't say reverse biased or forward biased. We can only say biased. Do you know one thing? When you say biased, I mean only voltage given. We can't say whether it is forward or reverse. Because you understand one point here. When there is a channel, semiconductor material, some voltage given, you can't say forward or reverse. And indirectly I am saying once for all, where there is no junction, please don't say forward or reverse, but rather say just biased. Output is biased, because even in JFET we can't say forward or reverse. Whereas in MOSFET it is also we can't say. Indirectly speaking, input is for reverse and output is just biased in FET, whereas in MOSFET both are just biased. It acts as a capacitor because in the JFET junction is acting as insulator, whereas in MOSFET it is also a capacitor, whereas it is simply called, it is not because it is acting something, it is silicon dioxide layer is itself an insulator. Insulator. Fifth point, switch. JFET can be used as a switch beyond VP. It's a better switch, particularly MOSFET. Enhancement MOSFET is the best switch because enhancement MOSFET has something called threshold voltage. About the threshold voltage, it becomes on. That's why by default today, if anybody asks you bring electronic switch, it's nothing but eMOSFET. Not diode, not BJT, not even JFET. The best is eMOSFET. As an amplifier, JFET is an amplifier, MOSFET is also amplifier. In JFET, output current is less, in MOSFET also output current is less. That's one of the limitations of FETs. Noise immunity is high in JFET, in MOSFET is also high. So this is the comparison between JFET and MOSFET. Secondly, classification of MOSFET. MOSFETs are enhancement MOSFET. There is no permanent channel, so this is dotted line. What is this arrow? Arrow shows conventional current when the junction is forward. So when the junction, you see this is N material. When it is N channel, you can tell it as negative, forward biased. When it is forward voltage, the current goes from here and then comes here, this is the arrow. Similarly here, current comes here. The only difference between eMOSFET and DMOSFET, there is a permanent line and there is a small dotted line. In DMOSFET, depletion mode, in a eMOSFET, enhancement mode. So these are the two modes we have in this. So there's a classification of MOSFETs. So today we are going to concentrate only on enhancement MOSFET. Please understand, most of the books and treatment they give is a very less treatment for FETs. But I'm here wantedly trying to increase this good weightage for FETs also, just like BJT. So enhancement MOSFET, we call it here. Look at this. This is N, drain, N, source. Source is grounded. This is VGS. And current is flowing. Electrons are here. They are trying to go from here through here, but there is nothing here. This is not there physically. Originally it is not there. It is only induced for VGS positive. That's why I have kept this as a dotted line. This is aluminum. That's why it's called metal oxide semiconductor. Once again, metal oxide semiconductor. That's called MOSFET. Okay. This is silicon dioxide layer. This is substrate. Substrate is generally taken heavily doped. You know why? Substrate is taken heavily because when this is heavily doped, it pushes this individual channel here. Otherwise, the individual channel will be spread over the entire substrate. If this is pushed onto between the drain and source, what happens is, if it is pushed between drain and source, there will be a good amount of current there. That's why wantedly substrate is heavily doped. Another thing the students are asking me, sir, why this is a semiconductor? After all, it is a substrate. Can you make a metal there? Because they want to put a metal and make it as a cheaper. But the point is, if you put a metal and there you have to get the carriers here. Depending on the VGS, if this VGS is positive, it should produce negative. That are minority carriers of substrate. If this is negative, if VGS is negative, this is supposed to produce positive. That is majority carriers of them. Therefore, if it is a semiconductor, then only it can supply two types of carriers. Depending on the gate supply, it has to give two types of carriers. If two types of carriers are given, you need to understand, to be given, this has to be semiconductor but not the metal, because metal can only give electrons. Metal can only give electrons there. So therefore, substrate has to be semiconductor and substrate should also be heavily doped, and this is channel to be induced. And you know why this carrier is getting induced? The answer is very simple. This is a metal, this is silicon dioxide layer, another semiconductor. These two are acting like a capacitor plates, and therefore when you give positive, negative is induced. When you give negative, positive carriers are induced. Therefore, capacitor action is working there. For this, I have made a small table for you to understand. Now please follow me as I explain the operation. Let me explain the operation. For that, I have taken a table here, VGS, effect, ID. If VGS is less than 0, when you give negative, positives develop. That means holes developed between source and drain. If holes are developed, there is no connectivity between source and drain, because if you see here, source is a N, drain is N. Between that you need electrons but not holes. So therefore, when you get electrons, then only there will be a connection. But here, when you give negative supply, you are getting holes between drain and source. Then this is ID 0, because they are not connected. Then if you give VGS 0, no holes, no electrons. Therefore, source and drain are not connected. Still they are not connected. When you give positive, opposite carriers means electrons develop. Therefore, source and drain connected, ID will flow. But for what value of VGS ID will flow? Suppose if one electron comes between source and drain, will it flow? 2 electrons come, 3 electrons come? No. There have to be more number of electrons. And there should be sufficient number of electrons. That sufficient number of electrons till they form that voltage is called threshold. Threshold voltage is the minimum voltage from which conduction starts. That's why you should go on giving positive voltage till the sufficient number is formed and current is sufficiently coming up. That's called threshold. This VT is threshold. It is a minimum voltage required for drain current to start. I have given a curve here, you see there. Suppose this is 1, 2, 3 and VGS is here. Starting from 2, good enough is 3, large value at 5. This is current in milliamperes. This transfer characteristics. What happens is, you can always calculate change in ID by change in VDS, that is approximately 2 milliamperes per volt. 2 milliamperes per volt. That's about transfer characteristics. Then let me go for output characteristics. That is between VDS and ID, just like JFET. The only difference is here in the MOSFET you are giving it, they are working for positive voltage. That's why I took positive VGS, VT here. Please remember. Then when you go to characteristics here, output, when VDS increase, ID increase. At some point they become more and more. When the carriers are increasing, we normally think current will increase, but because of collisions, current is decreased. And because of when the VDS is increasing, current is increasing, but they get collided. When they get collide, you know what happens? When they get collide, what happens is, what exactly happening is, there is a no movement or restricted movement. That's called velocity of the carrier is saturated. When the velocity of the carrier is saturated, it is called saturation region. Saturation region. Velocity is saturated. So VGS1 is greater than VT, VGS2 is greater than VGS1. That means this is the lowest VGS we can take and higher is going. So as VGS is increasing, ID is increasing. So here is a drain resistance change in voltage by change in current in saturation region, because the saturation region is called constant current characteristics. I have been telling you, in BJT, active region is called constant current characteristics. In JFET, pinch-off region is called constant current characteristics. In MOSFET, it is saturation region called constant current characteristics. Therefore, wherever the current is constant character, it's acting as a transfer of resistance, and hence it is acting as amplifier. Look at here. As voltage is increasing, current is constant. When voltage increasing, current is constant. That means internally what is happening is resistance is transferring from one value to the other. From lower value to the higher value, resistance is transferred. That's what happening. VGS1 is greater than VT. And this is the region where we have to calculate two values you can take for change in ID here and change in VDS here. Change in VDS, from there you have to take change in ID. This value and this value. So this will be approximately 10 kilo ohms. This is about RD. The fact of the matter is you can also calculate GM. For example, this one ID1, ID2, VGS1, VGS2, change in VGS by change. So if you take two characteristics and ID, you will get GM. If you take one characteristics and ID, you will take RD. So this is what I mean by output characteristics. So generally ID is function of VGS and VDS. If you draw between ID and VGS, it is called transfer characteristics. If you draw between VDS and ID, it is called output characteristics. As already said, initially for every increase in VDS, there is almost equal increase in ID. But as VDS increase, current increases and collisions come. When the collisions start, velocity is saturated, and that is called saturation region. Then, now let me talk for a while for different devices that are working as an amplifier. Amplifier in BJT, in active region it works as an amplifier. FET, in pinch-off region it works as an amplifier. MOSFET, in saturation region acting as an amplifier. That means all parameters you are calculating for all these three devices, you should call it as, you should take in these regions only, because only in those regions they are acting as what you call, they are acting as amplifiers. Now let me take you for VI equation. After VI characteristics, I generally go for VI equation. ID is K into W by L, VGS minus VT, VDS minus VDS square by 2. If ID is equal to K into W by L, VGS minus VT into VDS minus VDS square by 2. If VGS minus VT is equal to VDS, That means this is a condition for saturation region. If I substitute this value here, what do you get? K by 2 W by L VGS minus VT whole square, where K is mu n epsilon by D. What do I mean by mu n? Why do I take mu n? Mu n I take it because it is n channel. Epsilon naught, epsilon r is nothing but silicon dioxide layer by D. D is the height of the gate. So remember here, W is width of the gate, L is length of the gate, and D is height of the gate. Keeping these things, we get the characteristics and then the VI equation here. With that, we will go to illustrative problems because concept is more illustrated now in terms of some more problems. Okay, let's go to illustrative problems. Can we calculate GM from output characteristics, even from two curves? For example, ID versus VDS. This is a 5, 3, 4, 3. For example, 4 minus 3, change in ID, 5 minus 3, change in VGS. So 4 minus 3, 5 minus 3, 0.5 milliamperes per volt. So we can also calculate GM from output characteristics. Can we increase drain current? If you want to increase drain current, the first option is W increases, but size increases. That's very bad. We are in the days of VLSI and where size has to be small. If L decreases, then source and drain may get shorted. That is also a problem. If D decreases, the capacitance increases. If capacitance increase, we have so many drawbacks. Rise time increases, bandwidth decreases, impedance decreases. When impedance is decreasing, it is as good as this is shorted. You will give a signal, you will be waiting for output. You don't get any output, because input itself is not given. You think input is given. If the capacitor is shorted, it started here and here, nothing goes there. That's meaning of what you call short circuit. Question number 3. The output VI characteristics of an enhancement type MOSFET has A. Only anomic region, only saturation region, anomic region at low voltages followed by a saturation region, anomic region at large voltages preceded by saturation region. No. Option is C. Initially, it like a ohmic region, and then as current increases, carriers increase, collision take place, velocity saturated. That's why it is called saturation region. That's why the option is C. You look at here. As VDS increase, initially current is increasing. At later part, it is gets saturated. So this region is called ohmic region. So we can also call this as non-saturation region. So ohmic region is generally used in JFET, but in MOSFETs we call it as non-saturation region because velocity is non-saturated here, velocity is saturated here. Option is C. Question number 4. In modern MOSFETs, the material used for the gate, what are the options? High purity silicon, high purity silica, heavily doped polycrystalline silicon, D. Epitaxial grown silicon. Epitaxial grown silicon. In modern MOSFETs, heavily doped polystyrene silicon material is used for gate, and the option is C. Question number 5. In order to protect a MOSFET against damage from any stray voltage at the gate, in order to protect a MOSFET against damage from any stray voltage at gate, grounding the rings are provided, terminals are shorted, source terminal is earthed during the transit, None of the above. The options are: in order to protect MOSFET against damage for any stray voltage at the gate, source terminal is generally grounded. That's why by default and most of the time source is grounded. That's why source is generally grounded to avoid these stray problems. If you look at this manufacturing of this, we can see ground there. Option is C. Sixth one. Draw the symbols for N channel and P channel enhancement MOSFET. What are the symbols for N channel, P channel MOSFETs? For example, here, drain and source. This is N channel. As I told you, in MOSFET there is no channel permanent. Channel is always induced. That's why you have to go for dotted line. So all are dotted lines, all are MOSFETs. So current is going in is called N channel, going out is called P channel. This substrate can be a separate, but sometimes they both are shorted. As I just told you now, source is generally shorted, so substrate is also shorted. That's why generally these two are generally connected. If you want to give any other voltage externally, you want to keep it separately also, you can give, but generally they are connected and both are shorted. This is the meaning of what you call. And you see this gap between is silicon dioxide layer. Silicon dioxide layer. So gate, inducer channel, silicon dioxide layer. Linked question. When gate to source voltage of a MOSFET is 10 volts, that means VGS, drain current is 3 milli, and the average threshold voltage is 3 volts. Seventh problem. Calculate the resulting value of K for the MOSFET. Eighth one, from the transfer characteristics. What I mean is, in your solution, we know that ID is K. You can call it as another constant, K by 2, another constant, into VGS minus VT whole square. Then what is ID? 10 milli given. Then K we have to calculate. VGS, VT. So look at this data given. Current is 3 milli. VGS is 10. So that is 3 milli is equal to K into 10 minus 3. So 3 by 10 minus 3 whole square. This is a way you can calculate K. Once the value of K comes, that K value you can substitute here. When you calculate this K value, substitute here VG minus 3. Now he says the ID value also, any new value of ID you can calculate. Now look at this actually. ID is equal to this much. For this way, you need to draw the transfer characteristics. Shall we draw that? Suppose VGS is 5. The same current will become 2.44 milli. Similarly, for VGS 8, 1.52. So the whole idea is different values will give you different currents. And if you can plot it, you can have at 3 volts, you have this. At 5, 3 volts is the threshold. At 5 we have calculated, at 8 we have calculated, at 10 we have calculated all these values. So this is called transfer characteristics we have estimated. Problem 9. Draw the transfer characteristics for N-channel enhancement type MOSFET from drain characteristics. From drain characteristics, you try to estimate transfer. As I already told you, there is a way to estimate transconductance. Similar thing he is asking. Look at here. This is output characteristics. Take the values each. What is the value of current here? For VGS 3, VGS 4. So take different values and draw this curve. What is the minimum value? 3. That means at 3 you are getting some current. 4, for 5, for 6. For 6 the current is 5. Like that you can put these values and draw this transfer characteristic. That is called transfer characteristics from drain characteristics. Problem 10. In N-channel enhancement MOSFET at a fixed drain voltage, the drain current is maximum at 0 gate voltage and decreases with applied negative voltage. The drain current has a finite value at 0 and increases with or decreases with applied voltage of proper polarity. The drain current is 0 at gate 0 voltage and increases with positive voltage gate. The drain current is 0 for negative bias to voltage and increases with negative bias in this. I only want to tell you, you have seen the table, VGS negative, no current, VGS 0, no current, VGS positive, there is a current. Same logic we are going to say. In N-channel MOSFET at a fixed drain voltage. Why I am saying fixed? Because ID is function of VGS and VDS. So what to do when you are drawing for ID and VGS, the value is fixed. Fixed value. That means when he says VDS fixed, he is drawing for transfer characteristics. At fixed drain voltage, the current is 0 at 0 cut-in and increases with positive voltage. Therefore, option is C. Option is C.